The next example I want to do is one that you could have already done before. In particular, you could use conservative vector field, simply connected domain, curve arithmetic type stuff to figure this out. So in that sense, this isn't anything new. But what I want to do is I want to use Green's theorem to give you an alternative and arguably much faster solution. So we have a region D shaded in pink. We also have a vector field f defined on this domain. Again, I'm not telling you what f is, it's just some abstract vector field. The only thing that we know about it is that the curl is 0. And there are various curves a, b, and c. I'm telling us that the integral of f over a is 2, over b is -3, and the goal of the problem is to find the integral of f over c, which is this green curve. Like I mentioned, we don't need Green's theorem to do this, and you could have done this using conservative vector field theory. What you would probably do is you would probably draw in 3 different curves in purple here, and then locate 2 bigger curves in simply connected domains. You could conclude that the vector field is conservative on some region containing those closed curves so that the integrals are 0, blah, 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 do curve arithmetic and go from there. But what we're going to do today is apply Green's theorem to this region D. Green's theorem says, again, I'll just write down the abstract statement, that the double integral over this region D of the curl of f equals the integral of f over the boundary of D. Now, we're told that the curl is 0. So this term is 0, and that means that the double integral on the left-hand side is 0. So in other words, what we know is that the integral of f over the boundary of D is 0. And what I'll do next is the same kind of thing that I did in the previous Green's theorem examples, in that I'll think about the boundary of D and how to describe it using the names that we already have. So here's what I mean by that. If I were to redraw the region D in purple with no arrows on the boundary curves, and then I wrote down boundary of D, its orientation is defined such that the region D is always to the left. That means I would orient this outermost curve counterclockwise. This is how I would walk in order for the region to be on my left. But for the inner loops, these would actually be oriented clockwise. If you walk counterclockwise along those loops, the region will be to your right, and that's not what we want. So all of that is to say that the boundary of D is this oriented curve in purple. But now compare this to the original picture we have. The outer loop agrees with A, so we would get a plus A. It also agrees with B, so we'd get a plus B. But then C is traveling in the opposite orientation of the corresponding loop in the purple picture. So we'd get a negative C. And so the boundary of D as an oriented curve is A plus B minus C. And from here it's simple curve arithmetic. The integral over the boundary of D is 0. Well, the boundary of D is A plus B minus C, so this tells us that the integral over A plus the integral over B minus the integral over C is 0. And now it's a simple algebra problem. The integral over A is 2, the integral over B is -3. So solving for the integral over C, we get 2 plus -3, which is -1. Easy. This last example is more on the fun side. I don't think it's a typical kind of Green's theorem problem. It's just a cute application of the theorem that turns out to work really nicely in this specific situation. Which is, we're given a vector field, x squared y minus y, and negative y squared x. And we're supposed to find the closed counterclockwise oriented curve, C, which maximizes the value of the line integral of this vector field over that curve. That's an odd prompt, so let's just think about this for a few seconds before we actually move on to make sure we know what we're trying to do. We're given a vector field and we're allowed to draw any oriented counterclockwise curve. For example, I could draw a curve like this, and then we could compute the line integral of f over that curve. And maybe we get 10. And we say, great, I wonder if I can get a bigger number using a different curve. So maybe I draw a weird curve like this, and then I compute the line integral and I get 40,000. I say, okay, great, I found an even bigger number. But can I get even bigger? You know, and maybe you draw a curve like this, and it turns out that the integral over that curve is 10 gazillion or something, etc. So the goal here is to find the curve that gives us the biggest possible integral. Now, I find a problem like this pretty interesting because I don't know how I would approach this in general. This seems like a very hard problem to get your hands on. If you think about it, it seems kind of weird, like how would we go about finding a curve which makes this integral as big as possible? There's so many curves out there, and depending on what the vector field looks like, this could seem hopeless. So like I said, it's just kind of a cute solution that it turns out Green's theorem works really well here. So how do we make this work? Because we don't know what the curve is yet, we're going to keep things abstract in terms of a curve C. If I draw any counterclockwise closed loop, I'll let D be the region enclosed by that loop. So just for example, I could draw a loop like this, and D will be the region enclosed by it. What would Green's theorem tell me in this situation? Well, C, by definition, is the boundary of D. So Green's theorem would tell me that the integral of f over C, which is the thing that we ultimately care about, right? This is the quantity that we're trying to make as big as possible. This is the same as the double integral over D of the curl of f. So let's just pursue this road and see what happens. The curl of f is the x derivative of f2 minus the y derivative of f1. That should be negative y squared minus quantity x squared minus 1. And if I simplify this a little bit, we'd get 1 minus x squared minus y squared. So the idea now is that instead of trying to maximize the line integral, it might be easier to think about maximizing this double integral. In other words, we want to find the region D, which makes this double integral as big as possible. Well, let's think about what this double integral is measuring. It's measuring the signed volume under the graph of 1 minus x squared minus y squared over whatever the region D is. So let me draw a picture of the graph of the integrand. You would get this upside down parabolic shape. And the question is, what region could I compute a double integral over that would give me the most signed volume? And if you think about it, if you were to integrate over a very large region, like a huge disk or something, you could potentially be accumulating a lot of negative volume, because as soon as your region extends past the intersection of this blue thing with the xy plane, the volume beyond that part is going to be negative. So we probably don't want to include any of that. And by that logic, you can just see that the region which is going to give us the most signed volume is exactly where the blue thing intersects the xy plane. That would be the unit disk. I'll let you think about that for a second. And there we go. We're pretty much done. That's the region D which gives us the most volume, but the curve we're looking for is the boundary of that region. So that tells us that the curve that maximizes this line integral is the unit circle oriented counterclockwise.